Hi everyone, welcome to this lecture 8 of the course Ordinary Differential Equations. So today we are going to move forward. So So we've done this exercise, and then we want to perform numerical simulations of this system. So yeah, that's it. So that's the exercise that we are going to do now. All right, so we are going to perform numerical simulations of the system. So here, two things. So I've already shown you this program. So it's a C++ program. And here you have the heart of the Runge-Kutta-4 method. And so here is defined my iteration with function f and function g. All right, so my function f and function g are there. And as you can see, it's just a linear system, but I have to precise to set the right values of a, b, c, d. And as you can see here, a equals 0, b equals -1, c equals 2, and d equals -3. So that's the right matrix A. All right. So now let's go. Basically, we are going this program, and we are plotting the results in this file. And here are the initial conditions. Okay, so let's go. I run the program, right? Okay, so it's done. Now I'm going to see the solution. All right, so let's make a plot. So I use this small software. It's not small though. This software GluePlot to visualize the solutions. And so I'm going to plot in the phase space UV or XY. So sorry, it's this file. All right. So this is the trajectory. So I'm going with time. If you remember, the solution is going to 0 and is doing like that. All right. So I'm going to try to visualize numerically a few solutions that are relevant with respect with the picture that we draw at the lecture 7 last time. All right. So for example, I can draw another solution. So I could start with a value, for example, 1, 1. So if you remember, in the neighborhood of 0, 0, the solution should be tangent to the eigenvector associated with the smaller eigenvalue in absolute value. So let's draw this eigenvector. So I'm going to draw this one. All right. Yeah, so you can see it's tangent. We can maybe focus a little bit. We can focus a little bit. So, for example, so I'm just zooming a little bit. All right. Okay. So it's a little bit too small. Okay, now if you remember, we had the null line for the y. So the null line for the y was y equals 2/3 of x. So I can plot also this null line, which I will write 2/3 with that. Okay, now what you can see here is that two things. So when the trajectory crosses the y-axis, which is here, the direction with respect to the x-axis changes. So here I'm increasing with respect to x, and then when I cross the y-axis, I change. And here, when I cross the second null line, the direction with respect to y changes. So here it's increasing in y, but when it crosses this null line, of course, it becomes decreasing. All right, and then it sticks to the. This is a trajectory. This is my eigenvector, and this is also a trajectory actually. All right, and I can write also the other trajectory, which is 2. While the other eigenvector is 1, 2. So I can also plot this one. All right. And for example, I can choose a solution which starts, let's say here. And I should see a solution that is going to stick there also. So let's try a solution. For example, I will start with, as initial conditions, I will choose 0.1 and something a little bit smaller than 0.2. So let's go back to that. I'm going to plot it in another file, and I'm changing my initial condition. So I'm going to choose 0.1. And for example, here, 0. And I'm going to run that. Okay, then I'm going to plot again the same thing, but I will add my other trajectory all right, so oh, it's a little bit too small. Can't see that. Okay. So I need to change that again. And, yeah, we cannot see. This one is too. So let's do it again. So I start. Okay, let's do it again because we don't see it. We don't see the solution here. So it's two here. Just okay. Let me just look at what's going on here. Okay, now you can see that's what I wanted to show you, that here now there are two trajectories, but I needed to make a zoom to show you that the second trajectory is also tangent to the first eigenvector here. See? All right.
Excuse me, teacher.
Yes.
Is all those lines are trajectories?
No. So one. So
the purple one.
Yeah. So the purple one is a trajectory. Is the trajectory which lies in the eigenvector associated with our vector that I called V2. All right.
Okay.
And then all the trajectories will go towards zero, except a specific one in the direction tangent to this eigenvector. You see, the yellow one is a trajectory and the green one is a trajectory. So sorry, the purple one is a trajectory. It's not, it doesn't lie in the in the eigenvector, but it's very close to. So the eigenvalue is the eigenvector. It's actually it's the other one. You know, there are two that, so it's green, I guess, here, right? Okay, so in green, it's a specific solution that we computed. It's the trajectories associated with V2, right? It's a very specific. And you have another one, which is the orange one. It's the trajectory which lies in V1 here. So here, yeah, you have a trajectory. I could draw a set here. And then the yellow and the purple are other trajectories starting with another initial conditions. But as you can see, asymptotically, they are tangent to V2. All right. So this it relates to the picture that we draw the other time. So I could add a few other solutions and to draw the same picture as we did last time. Is that clear?
I'm trying to understand.
So this illustrates the stable node, right? When you have two eigenvalues that are real and negative, we call the stationary point a stable node. Right? And here it's the case where the two eigenvalues are different and negative. So we are now moving forward and deal with question 2. So let's do that. All right, so let's do it general. It's just a change of variable and diagonalization of matrices. So, span. So we're solving x prime equals ax. But so we have two eigenvalues and two vectors. So if I write P as the matrix which components are V1 and V2, so I know that my matrix A can write P, D, P minus 1, where P minus 1 is the inverse of P. So I can write x prime equals P, D, P minus 1 x, and therefore I have that P minus 1 x prime equals D P minus 1 x. And so here, if I call that y, I obtain y prime equals dy, right? So now I recall that, yeah. So if P here is V1, V2, so V1 is 1, 2, and V2 is 1, 1. And so P minus 1 you can compute that it's minus 1 times, so 1, 1 minus 1 minus 2. All right. Okay, so now, yeah, and then, so now, so here d equals minus 2, 0, 0, minus 1. And so I can compute easily the solutions of dy, which are, so let's say 1t equals so here I can write simply, I can see that y1 of t equals y2 of t squared. So we already did that almost. And here, so I have to put that. So if you remember, okay, so I can plot that. So I should obtain, I don't know if I have a solution here. So if I put here, it's my y1 and here is my y2 here, I have something like that. Okay, so let's try to run. We're going to compute that. So we are going to make simulations again around that. All right, so I'm coming back to my program here. So I'm going to change it. So now what you have is that a equals minus 2, p equals 0. So of course here I can compute directly because it's I know the solution explicitly, but let's run the simulation. So, and d equals minus 1. So now here my matrix is the G matrix with the eigenvalues on its diagonal. All right. And okay. So, all right. I can do something now. Right. So, for example, the first initial conditions that I chose was u equals 0, u equals 1, and b0 was so let's say so this is too close. No, v0 minus 1 and v0 minus 4. Okay, but I want to see this solution, but in the y variable. So I can do this computation. So here, I change. So here it's so I want here my p minus 1. So you know the p minus 1. So it was So p minus 1, it was so 1, 2, and 1, 1. So here it's 1. Minus 1. And here it was 2. All right. So what I compute here is my y equals p minus 1 of x, if you want. And then I will start with x0, y0. All right. And then let's put the result in there. And let's go. Let's compute that. All right, and let's look at the result here. Okay, you can see that, yeah, so as we saw, yeah, it's kind of a square. You have y1 is a square function of y2, all right? So this is the solution in the y variable. Now, if I, of course, if I set x of t equals p times y of t, I should recover my previous trajectory. So let's do that. So now I'm going to change my print. So now I will also write for each y of t, I will write p times y, which should make x. So my p was the vector 1, 2. So here it's not a good 1, 2. And the second vector was 1, 1. So now if I do that, I'm running the same thing, but instead of just printing, I'm going to print the 4 numbers, right? So here it's the solution in the y variable, and here, so capital Y, right? And here it's the solution of my initial problem in the x variable, right? So let's do that. I'm going to run again the program. Yeah, I can write it. Okay. So again, so if I write that, it's the same as before. But if instead I plot 4, 5, I should recover my initial trajectories. And yeah, that's not bad. All right. So my initial condition was what? Was -1, -4. No, it's weird. So let's do something. So yeah, I forgot the minus, the sign minus. So now I put the sign minus here, and we're good. So now here I recover the trajectory of my original problem, but I didn't compute it directly. I computed the solution with the diagonal system, and I recovered it by using the equation x equals py. And there's an equivalence linear transformation from solutions from one system to the other. So now if you have any question, please go ahead. All right, so next we are talking about unstable node. So you could do the same exercise. If you observe this system 3.7, it's the same as 3.5, but I just multiplied the two equations by minus one, all right? So which means that the trajectories will be the same, but the direction is the opposite. So you just change your arrows on the other side. So instead of going towards 0 when t is going to plus infinity, you're going to 0 when t is going to minus infinity. All right? And so I'm not going to solve this one because it's exactly the same, but at the end, you just change the directions of the arrows. All right? Is that clear? So I let you think about that. And if you have any questions, sorry about that. Next time you can ask me. All right? But so in this case, you will find instead of eigenvalues -2, -1, you will find eigenvalues 2 and 1. And it's called an unstable node, right? And it's a source. So an unstable node is a source, but a source is not necessarily an unstable node, meaning that a source contains unstable nodes and other things. Okay, so let's move forward. And now we are considering complex eigenvalues. And I let you do the same exercise with this equation now. So try to compute the solutions and then draw it. Okay, so I let you 10 minutes to think about that. All right, so now we are considering this equation, which is associated with this matrix. So now, if I try to do the same thing as before, so let's compute the eigenvalues.
Monsieur, c'est 0, 1, moins 1, 0, non? La matrice.
No, this is the matrix. 0, -1, 1, 0.
Parce que je pense que vous avez changé le système.
Oh,
C'est parce que j'ai...
maybe.
No,
No.
it's clear. It's 0 minus 1. X prime equal 0 by x minus 1 by y. First line, we be 0 minus 1. The determinant will be lambda square plus 1.
Yeah, that's right. So no, we are considering this matrix, right? That's the one which was in the slides. All right. No, this is the exercise that I want to do. All right. So let's move forward. You can do it in live. So now, exactly, we will get this expression for the determinant of A minus lambda identity. And then, so I have two complex eigenvalues, because all right, so now, so maybe some of you tried to do the same business that we did before. So you compute the eigenvectors and that stuff. However, be careful. We're looking for real solutions. So we could do that, but be careful. We are looking for real solutions. So it's not exactly the same thing. And I will come back at the end with a remark on that. So here, to solve this system, actually the system is simple to solve. So again, I write it. I can just do this trick because I'm looking for the solutions in the plane, so I can write it like that. I just sum up the first and the second. The second I multiply it by I, the complex I. So I get and this is nothing but I times x plus iy. So if I call it this z, I get in the complex plane z prime equals I z. And so everything works the same. So I can write z of t equals z0 exponential it. And I got the solutions here because this is just a trick that I did. So because z equals x plus iy, but so if I take the real part and the imaginary part of this quantity, I got x and y. So I can do that. So means that so x of t equals the real part. So and z0 equals x0 plus y0. So I get so it's the formula for the real part of the product of two complex numbers, and the yt will be nothing but the imaginary part. So it will be x0 sine t plus y0 cos t. So I can write that in this form with a matrix. So it's a rotation matrix. So I get cos t minus sine t and sine t cos t times my initial condition x naught. All right. So you have this one, or this one is very good. I like it. Okay, and then it's easy to represent those solutions. What are the solutions in the plane if I want to draw it? So those are the solutions. I pick up an initial condition. This is my Z0. And so my solutions are like that. It's a circle, right? So let's do it better since I have this opportunity there. Oh. Oops, sorry. Let's draw that. So it's a circle, right? The solution lies on the circle. Okay, and okay, and so for example, if I start here, or x0, y0, is my solution. If I pick up another initial condition, sorry. Oops. All right. So those are the trajectories of my ODE in this case. All right. Yeah, so thanks here, of course, the eigenvalues are complex. They are I and minus I. So next, we are doing the same exercise, but here, my matrix is given by A, B minus B, A, where A and B are real values. All right. So see you in a little bit. So now we are considering this equation. So if I compute the eigenvalues, so let's do it determinant of I minus A minus lambda identity. This is equal to IA minus lambda square plus B square. So if I want that to be 0, this means that A minus lambda square equals minus B square, which means that I have A minus lambda, which is equals to IB, or A minus lambda equals minus IB. So which gives lambda equals A minus IB, or lambda equals A plus IB. Okay, though again, the eigenvalues are complex and conjugate because I consider here only real matrices. And so let's do the same computation as before. So if I have x prime equals I x plus by and y prime equals minus bx plus ay, I can sum up the two and multiply before the second equation by I, and I get this. So x times I minus a minus ib plus y b plus I a. All right. So then this is a minus ib times here times x. So let's do it. Plus, so if I put the I in front, I get a minus ib y. And so I get a minus ib times x plus iy. So again, if I call it z, I got z prime equals I minus ib z, and this gives z of t equals exponential I minus ib t z naught. And this is my solution. So c of t equals c naught exponential a minus eb t. So I can write it in the real part. So this means that that x of t equals the real part of that. So I can put exponential at in front, and this is x0 cos bt minus y0 times sine of minus bt, so which makes here a plus. And for the y, I will get exponential at minus x0 sinus bt. So the minus comes from sinus minus bt here, plus y0 cosine of bt. So it writes x of t equals exponential at, and here I got cos bt sinus bt minus sinus bt and cos bt. Times here x naught y naught. Now, if I want to draw that, if I want to make a picture of that, let's do it correctly. The y-axis, the x-axis, and so it depends. So, for example, I will draw the a and b, positive a and positive b, for example. So this is equal of So now I have a A. So assume that A, so let's do the case, no, A negative and B positive, for example. So the other cases are similar. This means that, well, the solution is going to 0, but it's going to 0 making loops. All right, so let's assume my x0 is here and my y0 is here. So I have my z0 here. So my solution will be like that, kind of. And so no, I'm wrong, because I told you that my B was positive, so I need to do that. Since my B is positive, but here I have a minus here, I'm going in the other direction, so I'm going like that. Yeah. So I'm going in the negative direction, and so since I have an exponential 80, the norm is decreasing and it's going to 0. All right. Now you can do all the possible case with A positive, A negative, B positive, B negative. All right. So in the case A negative, we have a stable focus, which is a sink. And in the case A positive, you have an unstable focus, which is a source. So stable nodes and stable focus are sources, or are sinks. They correspond to a negative real part for eigenvalues, while unstable focus and unstable node are sources, and they correspond to a positive real part. So next, I propose you the following exercise. So next, we are going the general case where we have two complex conjugate eigenvalues for the matrix A. And so the goal of this exercise is to show then that you can bring it to the study of the previous case. So the previous case is quite general, and you can bring the study to this case with a change of variables with a matrix P that you have to specify in the exercise. So I let you think about this exercise for the next couple of minutes. All right, so let's assume that we have the two-dimensional linear system x prime equals ax with two complex eigenvalues lambda equals plus or minus ib. Okay, which means what? Which means that we have a v for an eigenvector v equals lambda v. All right, so what I'm going to do now is writing what are the real and imaginary parts of those equations. So what do I have? I have that the real part of AV which is actually a real part of V equals the real part of lambda V. And the real part of lambda V is real part of lambda, which is A, minus, so let's consider A equals plus, right? It doesn't matter. So A times real part of V minus B, the imaginary part of V. So where V is my eigenvector, all right? So you have that A times real part of V equals A real part of V minus B imaginary part of V. And in the same way, you have that A times the imaginary part of V equals A times, so small a imaginary part of V plus B real part of V. Okay, so now I'm going to write that as a matrix equality. So I'm going to write that A times the matrix, so real part of V is a vector, and imaginary part of V is another vector. So here it's a matrix, a two-dimensional, 2 times 2 dimensional matrix. And here I'm going to write that. So I can write that this is real part of V, imaginary part of V as a matrix times A minus B and B minus A, right? All right. You know, because when you do this matrix computation, you have that A times this vector will be equal to the first column of this computation here. And if I do the matrix, the product of matrix here, the first column, you will do, so it's this equality, you can do it by yourself, corresponds to this equality. All right. So now if I call that D and this matrix P, so here my P is the matrix for which the components are the real part of V and the imaginary part of V. So I got that. So now I'm in the same situation as before, when I had like 2 negative real eigenvalues. But now my matrix D is no more diagonal, but it's of a particular type and corresponds to the previous exercise. So now if I start with x prime equals ax, and I set x equals py, I will get that y prime so I want p d, yeah, so it's x, so yeah, so it's not, so x equals all right. So sorry. Yeah, that's it. So finally, you have this equation with x equals py. All right. Yeah, so finally, you do have this expression for p. So p here is the matrix with the real part of V as the first column and the imaginary part of V as the second column. So next we consider this equation, and you should find two complex conjugate eigenvalues. So try to find out what is P, what are the trajectories for the system capital Y prime equals D capital Y. So this exercise is kind of an application of what we did previously.